Okay, so in this video we are just going to discuss, just move that out of the way for a moment, our next variable of interest, and it is a derivative of peak torque, in that it is a measurement that you derive from peak torque, but it is so often reported within the published literature it deserves its own video explanation here, and that is the agonist-antagonist ratio, in this case the hamstring to quadriceps ratio. And it's a very simple measurement to report in theory. The reason it's referred to on the report as the agonist-antagonist ratio and not the hamstring to quadriceps ratio is because the report doesn't specify the movement that's being assessed. So, for example, if you were performing internal and external rotation, in that case, the internal rotator muscles would be the antagonist and the external rotators would be the agonist. Or, for example, let's think with ankle inversion, eversion. The inverters may be the agonist and the everters would be the antagonists. So it depends on what sort of test is being performed, but this is reported in the literature as the hamstring to quadriceps ratio when we are looking at the knee extensors and flexors. Strictly speaking, we should call this the flexion to extension ratio because, as we've already discussed, while the knee extensors are indeed the quadriceps femoris muscle group, the knee flexors are the hamstrings, but also the gastrocnemius. So to say that it is the hamstring to quadriceps ratio isn't strictly true. It's the quadriceps, or sorry, it's the hamstring and gastrocnemius to quadriceps ratio, but I suppose HQ ratio is at least a bit snappier, if nothing else. So there is sometimes some confusion with how this is presented because you have two values reported down here for our HQ ratio. So we have 57 and 55 here, and no values here under the flexion set of columns for the right and left leg, and that's fairly straightforward to explain. That is because the value that we have here, let's focus just on the right leg for a moment. I'll just delete that there. The value that we get here for the right leg has been calculated very simply as this peak torque for the right knee flexion, or for right knee flexion, being 71.9, might as well call it 72, and we've divided that by the peak torque that we recorded for the right knee extensors. And just to prove to you that I'm not making this up, why would I? But 71.9 divided by 126.2 gives us 0.5697. That would be a ratio, but again, biodecs like to confuse things by explaining the measurement as a ratio and reporting it as a percentage, and we get a percentage of the HQ ratio reported as 56.973, which they've just rounded up to 57, which is absolutely fair enough to do. So the peak torque on the left hand side would be calculated, so 55 here, by dividing 66.6 by 121 Newton meters that we have here. So this gives us our HQ, in this case, ratio, or our agonist-antagonist ratios for the left and right limb. Remember that these are unilateral assessments, i.e. they are assessments of muscle function, agonist-antagonist function on a single limb, the left leg and the right leg. It's basically comparing the muscles front to back that perform opposing functions. Now, you're not given a this G value here is where we sometimes report a age-matched, gender-matched normative value. You've already been given this in the isokinetic theory session that we done, and those lecture slides are on Brightspace for you to access. You have them across a range of different angular velocities at a range or for athletic and non-athletic populations, and you can easily find this information online. You might find that there are some differences in more recent literature with more specific sample populations, but as long as you've got something to compare them to. So the hamstring quadriceps ratio that we've performed here is a concentric ratio. This is the least reliable of the HQ ratios that is reported within the literature. So you can have an eccentric concentric ratio where you eccentrically measure the hamstrings and concentrically assess the quadriceps. This is more reliable because it is more physiologically and biomechanically relevant to a movement that's occurring. When you concentrically engage the quadriceps to perform rapid knee extension and perhaps even hip flexion, say for example if you're kicking a ball, then the hamstrings are eccentrically contracting to slow that movement down, to apply the brakes, as one of my old lecturers used to say. He used to joke that if you didn't have your hamstring muscles when you kicked a ball, your leg would just continue to arc forwards and come up and you would most likely kick yourself in the face. Now that's a bit of an exaggeration, but it does indicate the role that the hamstrings play eccentrically during simultaneous hip flexion with knee extension. So because that's the muscle actions that occur during a kicking movement, a eccentric hamstring with a concentric quadriceps, then testing the HQ ratio eccentrically and concentrically is going to be more physiologically relevant. There is even research out there that suggests that a mixed ratio of different angular velocities, so for example testing the quadriceps at 180 degrees and the hamstrings at a higher angular velocity, is also a more accurate predictor of injury. And that's what the agonist-antagonist ratio is really used for. It is an injury prediction tool. And the accuracy of that prediction is increased with the mixed ratio, so mixed angular velocities, with the mixed muscle actions, an eccentric concentric test, and is lowest with a concentric test that we've done here. But we've done this for time constraints, practicality, and ease of testing. So it's not something that you need to critique so much in your data analysis. So what I'm saying is don't look at this and think, oh, well, this is just meaningless, it's rubbish. No, you can still infer information from it, and you should, but at the same time be aware and perhaps even mention in future testing you would perhaps want to consider an eccentric concentric test or perhaps a mixed HQ ratio to improve the accuracy and the predictability and reliability of this test. Regardless, we see a increase in the HQ ratio with increasing angular velocities. So as a general rule of thumb, this is between athletic, non-athletic populations and between males and females. So this is just a very general overview. We would expect to see at a 60 degree per second an HQ ratio, if reported as a percentage, of in the low 60s. As we go up to 180 degrees per second, we would expect this to rise to anywhere from 70 to low 80s. And at 360 degrees per second, we would expect to see an HQ ratio nearer the 90s. Low 90s, I should add. Again, this varies depending on your gender and your athletic experience. So these two HQ ratios we have here are worth noting and are certainly something that I would document if I was looking at this data. They are low. They are very low. These should be much higher in the sort of 80-90% region. And how you interpret this is basically, if you want a sort of layman's interpretation of how to explain this, what this value is telling you, so this 57%, it is saying that the hamstrings are 57% as strong as the quadriceps. So this 71.9, let's just call it 72. And this 126 Newton meters here that you've got for the quadriceps. What this is saying is that this is essentially 57%, the hamstring peak torque is 57% the quadriceps peak torque, whereas at a higher angular velocity of 360 degrees, this needs to be near 80 or 90%. So this suggests to me that at a higher angular velocity here, this athlete would certainly need to improve the peak torque that they can produce. So training their hamstrings at higher angular velocities, performing more explosive movements, trying to incorporate perhaps plyometric exercise to increase that rate of torque development, which will lead to a greater peak torque. But certainly this is something that would need to be addressed. And we would use this primarily as a predictor of the likelihood of hamstring strain and subsequent ACL injury. And as a result, if worst case scenario, let's say you have a full hamstring strain or tear that results in a full rupture of the ACL, this is going to cause subsequent damage to the connective tissue within the tibiofemoral joint, possibly an MCL injury as well, because they perform similar functions in medially stabilizing the knee, and damage to perhaps the meniscus or even the cartilage and other connective tissue within the tibiofemoral joint. That's very much a worst case scenario, I should point out, but it is still theoretically possible. While this low HQ ratio isn't, and don't interpret this as, oh my god, this person is this is death by knee, as I once had a student describe it to me. Does this mean I'm going to die through knee injury? No, it is just a predictor of knee injury. It is not a death sentence by knee injury. But it is certainly something we would look to address. We would want to do more specific testing. So if you've got a bad HQ ratio with a concentric test, we would want to double check this with a more reliable HQ test, as we've previously mentioned. But because this is the least sensitive, if you've got that bad an impairment, that does suggest that there could be a real issue here with hamstring to quadriceps function. An alternative to this, which you could do, and I will end this video very soon, I appreciate this has been quite a long video, but you could also create your own HQ ratio quite easily by performing an average HQ ratio assessment. In the same way that we said we looked at peak torque and average peak torque, to the best of my knowledge, I don't believe there is much research out there about average peak torque, average HQ ratios, but certainly something to look into. I can't recall seeing it, but if we look at the average peak torque on the right limb for the hamstrings, so this gives us 65.6, and we divide this by the average peak torque of the quadriceps, giving us 113.6, then we get an almost identical HQ ratio to the peak torque value. And that is just another way of confirming what we've seen here. So with the average peak torque and the peak torque with a higher rep range, it might be worth just checking the average HQ ratio as well as the peak torque HQ ratio. But yeah, that is the agonist-antagonist ratio, and it is certainly something that I would expect to see, assuming there is a difference, I would expect to see in your reports somewhere.